Hello everyone, my name is Dian from Northeastern University. In this video, I will introduce our recent work, Policy Learning in SE3 Action Spaces. In the spatial action representation, some work uses a top-down image of the scene as the observation. Each pixel in the top-down image could represent an action targeted at the corresponding 3D location. A fully convolutional neural network is often used to generate a pixel-wise Q-value map. This is a nice approach because the fully convolutional neural network can generalize over different object positions. It also requires fewer action steps compared to the action space of the n-vector displacement. However, this approach is often limited to a 3D action space of x, y, theta, where theta is the top-down orientation along the z-axis. Besides, this framework also leads to a large action space so that it is hard for a DQ agent to find a good policy. In this work, we make two contributions. First, we propose a Q-function representation, ASRIC3. In this approach, the state space is enlarged in exchange for a smaller action space. It works in the 6-dimensional action space in SE3 and selects actions sequentially using 5 Q functions. Second, we propose a variation of DQfD that is better suited for the large action space. In ASRIC3, the first Q function Q1 is encoded using a fully convolutional UNet. It takes an input of a top-down image of the workspace and outputs the values for each xy position. The UNet also generates a state encoding EFS that will provide the state information for the other Q functions. We define an encoding function f2 that encodes the selected xy position into an image by cropping the workspace image center at that position. Q2 is encoded by a standard CNN that takes input of EFS and the image crop generated by f2. The output of Q2 is the values for each theta action at given xy. The encoding function f3 encodes the selected xy theta by first applying f2, then rotating the crop by the amount of theta. Q3 outputs values for each z action at given xy theta. Similarly, f4 and f5 keeps applying the successive transformation z and phi. Instead of using a one-dimensional image crop, f4 and f5 output a 3-channel orthographic projection image that can encode more action spaces. The output of Q4 and Q5 is the values for each phi and psi action, respectively. In the end, the greedy actions from all 5 layers combine the overall greedy action. Our second contribution is SDQfD, a variation of DQfD. DQfD penalizes at most one x per action with the maximum value, which is now efficient in the large action space. SDQfD penalizes all x per actions with a value higher than the x per value minus the marginal constant L, making it more efficient in large action spaces. We test our approach in a set of changing block stacking tasks in both simulation and the real world. The picture shows the target structures for different tasks, and the video shows one example run for building H3. We first test our approach in a SE2 action space of xy theta, then we test our approach in a 6-dimensional action space in SE3. In the SE2 experiment, the lab table shows the performance of different algorithms at the end of training. SDQfD works the best, and ASRIC3 improves both DQfD and SDQfD compared to the baseline FCN approach. The right table shows the time efficiency of ASRIC3. Our approach is much faster than the baseline FCN approach. In the SE3 experiment, in order to let the agent actively control phi and psi, we place 2 ramps in the workspace. Some objects are initialized on the ramp, and to offset the angle brought by the ramp, the robot needs to control the 2 outward plane orientations. The video shows some demo run when we apply the trained model on a real robot, and the table on the right shows the experimental result. The robot succeeds in 36 out of 40 runs in task 4H1. In task H3, the robot only fails in 1 of the 40 runs. H4 is the hardest task, where the robot needs to execute 10 actions to reach the goal structure. The robot succeeds 32 out of the 40 runs in H4. In IMH2, we use some unseen shapes during training for testing, and the robot only fails 1 of the 40 runs. Similarly, in IMH3, the robot also needs to construct using unseen shapes. The robot succeeds 31 runs here. In the end, we show the learner curves of ASRIC3 SDQfD compared with imitation learning baselines in simulation. The blue line, which is SDQfD, outperforms all baselines in all environments. To sum up, this work makes 2 contributions: ASRIC3, a Q-function representation for 6-dimensional action space in SE3, and SDQfD, a variation of DQfD that works better in the large action spaces. For more information, please refer to our paper. Thanks for watching.